So we are very fortunate to have Soonwon giving our QFarm seminar today. I had a little bit of trouble finding a formal CD from Soonwon, so what you're going to get is my summary of what I learned about him from the internet. The place to start is Soonwon was one of the MIT Technology Review 35 under 35. I actually don't know how many it was under 35, but he was one of them. He's been endorsed on LinkedIn for such skills as Microsoft Office. But in all seriousness, Soonwon is absolutely amazing. He's a quantum scientist of this sort of a leader in this new generation, connecting ideas in quantum information to quantum many-body physics and quantum computing. He was an undergrad at Caltech. We won't talk about what house he was in. From there, he was a grad student at Harvard, Lucan, and then a Miller Fellow as a postdoc at Berkeley. And he's now junior faculty at MIT. I think he's been there for like a year. So if you want to learn more about the job search process and what it's like to be a hotshot at MIT, he's also a good person to talk to. Anyway, we're very fortunate to have you here today to tell us about the science. So, you want to take it away.
Wow, great. Thank you so much for very accurate introduction. Actually, this is my second time being here and giving the QFarm seminar. And I'm extremely happy that, actually it seems like the number of people in the audience almost doubled. So like that tells me how rapidly this community is growing at Stanford. So I'm very happy. Today, I'm going to talk about some of the research directions that I've been pursuing for the past couple of years. The title of my talk is Toolbox for Analog Computing. Is microphone working?
Yes. Okay, you guys hear him in the back? Yeah.
I have a loud enough voice, so maybe. So let's get to watch analog quantum simulator. In my view, this is one of the most promising practical useful application of quantum science over the next maybe 10 years. So the idea is very simple. We build some quantum device, and this quantum device could be maybe made out of atoms or ions or some artificial atoms. And we have some tuning knobs, electric field, magnetic field, laser intensity, and laser frequency that we can tune over time. And the goal is we engineer those tuning knobs in a clever enough way so that the quantum system that we have is emulating the quantum system of the target that we want to simulate. Well, what are the examples of the platforms? Maybe the most representative one is the quantum gas microscopes. We generate the artificial lattice by optical lattice, and then we put the atoms and they are hopping around and emulate the motions of the electron in solid. And we can engineer the interactions and tunneling strengths and so on, and then take a snapshot. More recently, there are rapid development of neutral atom arrays. We have individual tweezers to trap the particles in whatever the geometry you want, and they use their internal quantum state as a quantum freedom. And these are not the only system. There are many other systems based on superconducting qubits, trapped ions, and solid state spins. And they have been already used for many interesting physics, probing say quantum thermalization, or some exotic quantum dynamics, like spin transport, or many-body scarring, or quantum phases and transitions. The natural question is, okay, what's next? It seems like it's already being a well-established area. So what can we do with this? One answer could be scaling up. Let's have a larger system size, longer coherence time, so let's just scale it up. However, I think that's a little bit too naive thinking. In real world, these systems are very heterogeneous. So not only have we to talk about coherence time and the system size, we should talk about what type of geometry we can engineer, what type of interaction we can engineer, how to perform measurement fast enough, or what are the range of parameters. There are many different qualifiers that limit the capability of devices. So in some sense, I think this is a defining feature of analog quantum simulation. We do not have full arbitrary digital control, but we have a somewhat limited controllability, and that's what distinguishes these devices from the digital devices. And the goal of today's talk is to talk about new theory development that's needed in order to move to the next stage in these limited cases. So here are the challenges and opportunities that I thought about regarding the analog quantum simulators. First, on the basic tools, we need to develop better basic tool sets. And examples are, for example, Hamiltonian engineering. Given the Turing knobs, what would be the effective way to engineer a target Hamiltonian as efficiently and robustly? Or benchmarking and characterization. And once we build a system, how can we characterize precisely and then calibrate them? And measurement tools that existing devices have a certain capability, can we do better than what we have? And the second branch of research would be identifying opportunities. Okay, suppose we have these quantum devices running in our basement. What should we do with this? What are the interesting physics questions that we can probe? Or maybe, and finally, what would be the new physics understanding? We develop a way to maybe approximate or understand what we have seen in the experiment, or how can we utilize for the practical application maybe quantum sensing. But those are the research topics that I'm thinking about on a daily basis in my research group. But today I'm going to talk about two works along those lines. One about the benchmarking and characterization, the other one more about the. So my talk is in two parts. One is part one, the benchmarking and quantum simulators based on quantum chaos. The second one is measuring arbitrary physical variables. So let me begin with the first part. And the first part is being has been done with large collaborators. The theory component is primarily done by my first graduate student, Daniel and Mark. And we have established collaboration with the two different experimental teams, both led by Manuel Andres and Oscar. So what do I mean by benchmarking in quantum devices? So ideally, we want to initialize some simple initial state, say O0. Here I'll talk about like qubit system, but majority of my talk doesn't care whether it's qubit based or particle itinerary particles, but let me explain the physics using qubit picture. So ideally, we want to prepare certain zero state and then evolve under unitary and then realize certain, the complicated, interesting many-body wave function. For the experiment, if you do this, initial state preparation is not perfect, dynamics is not perfect, and measurements are not perfect. So our goal is to verify whether we actually engineer the desired Hamiltonian accurately, and if not, how to quantify the amount of interference and noises such a way that we can calibrate the system. And one nice tool to have to do this task is estimating the fidelity. So in the middle, the raw experiment is the density matrix that's generated in the experiment. And psi ideal is what you wanted to generate in the absence of any header. And this fidelity is an overlap between those two, and this is what we call the fidelity. And if you can measure this fidelity easily, then this is very useful to characterize every other thing by calibrating. The challenge is this fidelity is extremely difficult to measure, especially when the controllability is limited. Let's talk about that. So what is the most naive way of measuring this fidelity? So one way is just perform explicit quantum state tomography. Just figure out what Go experiment is and then evaluate numerically the overlapping state. And how do we do that? We prepare some quantum state of interest in the experiment, and then perform many measurements so that we figure out the histogram for the different measurement outcomes. Okay? And if there's n particles, usually have an exponentially large Hilbert space. So for the generic quantum states, the probability of measuring different outcomes is order 1 over dimensions, 1 over 2 to the n. So if you have more than 2 to the n measurements, in principle, you can approximately figure out this histogram. And this histogram basically tells you the diagonal entries of the density matrix of the. But that's not enough because there are many more off-diagonal entries. And in order to figure out all off-diagonal entries, the most naive approach is to perform measurement not only in z basis but x, y, z basis for each particle separately. So we have 3 to the n different bases. And together we need to measure more than 6 to the n bases. This is a naive approach, actually modern, the way to perform tomography can reduce this number dramatically, but that requires running some quantum algorithm. So for now, let's assume this naive approach. So what is the 6 to the n? It's of course large number. If you assume 10 particles, it requires 100 million measurements. And if one measurement takes 1 second, this is already 2 years. But I would like to make one point. The 10 particle system is something that you can simulate on your laptop, right? So we don't expect quantum mechanics. The purpose of this part is we talk about small enough system size we can simulate. So we are not asking for the quantum mechanics. So nevertheless, just characterizing what state you have verified is extremely difficult. Not because it is difficult to simulate the dynamics, but because the number of measurements you need to take is large, and that concept is called the sample complexity. Okay? So that one of the primary goals that we face now is to reduce the sample complexity of estimating fidelity in this field at the moment. So there's a better way to estimate the fidelity, and based on randomized measurement. This is a video paper. So I'm not going to the detail, but I'll just tell you the final answer. So we again prepare the quantum state of interest, but instead of directly measuring the system, we apply the randomly chosen scrambling unitary UI, say U1, and then perform measurement in Z direction and get the binary B string, maybe 0, 1, 0, 1, and 5. I record what unit I applied U1, I record what measurement I got Z1. Repeat the same thing for different unitary U2 and obtain B string Z2. Repeat it m times and obtain m samples, and then put it to the classical computer and use some data processing, explain this paper, and then we can estimate the fidelity between the density matrix and the ideal quantum state they should have. Okay. In this way, they show that this estimation can be done very efficiently in terms of the number of measurements you need to do. So it's a sample efficient method. The problem is, how can we apply this randomly choosing unitary to the analog quantum simulator? Remember, we are talking about particles operating on optical lattices. What does it mean by applying random unitary on top of that, right? So we try to improve this protocol in a way it's applicable to the realistic systems. And here is our approach. So on the experimental side, we prepare certain initial state of interest. It could be a very simple state. It could be some complicated state that we want to study about. And then turn on the interacting generic Hamiltonian and it's ready to go. This Hamiltonian can be anything. The Hamiltonian you have in your lab at the moment is good enough. As long as this Hamiltonian is not fine-tuned to fail, then it'll work. And then after you use it for a sufficiently long time, so that obviously the title involves chaos, so you should have a time enough so that it's reasonably chaotic. And then perform measurements to obtain the bit strings for this particle number configuration measurement, Z1 through Zn. That's all we need to do on the experiments. And the rest is classical computation. The classical machine, what we are going to do is we consider the initial state and evolve under the natural dynamics of the Hamiltonian that we know. And then we need to do this classical computation, therefore it will be very expensive, exponentially. So this approach is not scalable for the quantum devices larger than what we can simulate. And we obtain these pure wave functions and calculate what would be the probability that you draw different measurement Z from if you are induced from this quantum mechanical wave function. And calculate Z, and also for the reason that I'm going to explain later, we'll just average this over different time t, so that we have a p average. This pz depends on the particular time evolution t, which is matched to the what we want experiment. This p average is time independent, it's average over time. And third step is combine these two information. So basically, we have a formula here. The detail is not so important because I'm going to explain the equation in the next few slides. But basically, we use these snapshots like Z1 through Zm and stick into the formula that depends on those values of the computation we do, such a way that evaluate the FP. And our claim is this FP approximates the many-body fidelity that incorporates not only the imperfect initial state preparation, but also the fidelity of the dynamics, and finally the fidelity of the measurement. So we argue that this works for the generic ergodic dynamics and have some proof in certain limiting cases. And this is expected to work when the amount of error is reasonably small. It doesn't work when the error is so large. And then this is a sample efficient. This can be this FT converges quickly to a certain number as a function of number of samples, and this is extremely easy to experiment and implement this experiment. Furthermore, this can be used as a further applications. For example, we know this dynamics has a very good fidelity because we are not fine-tuning anything. We just choose a Hamiltonian that's best in your lab. For that cases, if you assume that the dynamics is good, we can use this as a measure of many-body overlap between a certain state that you initialize the system and some state that theoretically you want to compare against. Or if you assume this initial state is something you can prepare very, very well, and then see how this fidelity decays by doing this for the different, evolve on the different times and they repeat this procedure, and then see how the fidelity decays, that way you can figure out the amount of errors that happens in your system, the dynamical process. And this is not suitable for the large enough system sizes for the reason that I explained, this computational concept. Yes, Christian?
Yeah, so you say that it works for generic ergodic dynamics.
Yeah.
Isn't that's like a simplifying assumption? That's not, because you're saying that you're measuring along a random unitary. If I'm sampling things, ergodicity helps me because it makes every state look like one another. Is that saying that it then doesn't work for some sort of integrable dynamics or something that's near integrable?
More precise statement is this. If you choose generic Hamiltonian, like interacting Hamiltonian, you can prove that it works with the probability equal to 1 in a certain parameter regime, say error rate is small and the evolution time is long enough.
Okay.
If it's not, we cannot prove, but our numerical simulation shows that it almost always works as long as it's not non-interacting particles. And the performance of our convergence rate and the accuracy and the systematic error and so on depends on how ergodic it is. More and more ergodic, it is better and better.
So what property are you actually going to use of your Hamiltonian dynamics?
Yeah, so they don't come in the theorem later, so I can talk about it later. I'll keep it in mind. Any other questions? Okay, so how does it work? It works because there are the so-called emergent speckle patterns that arise in ergodic quantum dynamics. To explain that, let's talk about what speckle-based benchmark. So this is an approach that Google has developed and actually used in their famous quantum schema paper. The idea is the following. Suppose we start from some initial state, apply randomly chosen unitary and perform measurements. And then, as I described previously, we have this histogram, and all different measurements comes out roughly 1/2 to the n, except not. Actually, some of the B strings are slightly more likely, maybe 2/2 to the n, or 0.7/2 to the n. It's a little less or like, and there's also some fluctuation. And this is what people call speckle pattern. So see, I'm so happy that I'm giving an in-person talk, but if you see this laser pointer, if you look closely, the brightness is not perfectly homogeneous, but you actually see some fluctuation of intensity on your laser. And that happens because this light path is not perfect, but there are many different paths that is rough surfaces and so on. So the different light paths interfere in a somewhat random way. So if you take the absolute square to calculate the intensity, and that has this random interference pattern. And that's called the optical laser speckle pattern. This is exactly the same origin in the many bodies. So we get the speckle pattern, and what's nice about speckle pattern is this specific pattern, like which part is bright, which part is less bright, is non-universal and depends on every single detail of the whole system. However, there are statistical properties. For example, if you compute the variance of the intensity over the whole surface, and that takes a universal value. In fact, if you plot the histogram of this intensity, that follows a certain distribution called the Photo-Thomas distribution, which is a fancy name of exponential distribution. But what happens if there are many different noises? Every time we run the experiment, different errors happen here and there. And what it means is, you will have an incoherent linear combination of these speckle patterns, effectively leading to the no speckle. And this is why if you have a lantern, incoherent light source, you have a homogeneous, intensity profile. So you do not have a speckle pattern. And if you compute the variance or the square here due to normalization, it's equal to 1 instead of 2. The variance is larger for the speckle pattern. Right? And the idea is to use this speckle pattern as a fingerprint of the desired dynamic that you want to implement. So what we do is we compare these two measurement outcomes from a noisy case, and then so here for P1Z is a probability that you draw Z from the experiment, and P0Z is a perfect case where we should expect a spectral pattern, and then literally compare their covariance and normalize by this number and then subtract 1, and it's equal to F. And turns out this formula is not an estimate, and you can rigorously prove with the proper bound in the case of random unitary circuits. So, however, it looks like we need to figure out the probability distribution P1 of Z. P0 of Z will be computed by computer, but the P1 of Z might sound like you can estimate by drawing many samples. Turns out not, because this whole expression is linear in P1Z. That means you just sample Z from the experiment, and regard this whole expression as a sample average of P0Z, which is the value, so we can do this. So if you have M samples, we have a sample average of this guy, and that converges quickly, and that's the sample, efficient way to figure out this. Okay, and that's the Y sampler. So suppose we want to generalize this approach to analog quantum simulation. So we have initial state, French dynamics under whatever the Hamiltonian you want, they obtain the B strings. Suppose everything is ideal and plot the histogram. And this histogram no longer exhibit the spectrum. The reason being, actually there are some systematic trend, for example. So these initial states happen to be low energy configuration. And if you time evolve, after some time, of course the B strings associated with the lower energy will have a higher probability to occur because of the energy conservation. Therefore, we do not have a spectral pattern, especially, and that's also true if you have extra symmetries. And if you have an error, the systematic trend is still there, so it doesn't change. But our idea is to do some proper data processing to extract spectral pattern out of this probability distribution, and then use this emergent spectral pattern as a fingerprint and do the benchmark. So more specifically, we'll talk about hidden spectral pattern. More specifically, it turns out this probability of measuring B string Z can be decomposed into the product of two factors. One is what we call as a P average Z that does not depend on the specific term, and P tilde of Z, which depends on the evolution time that we such a way that this P average Z can be obtained by just averaging the left-hand side over time. And then we have a systematic contribution that's kind of Boltzmann factor, and it reflects energy conservation and other symmetric considerations. And P tilde of Z is coming from the random interference patterns. And we can show that P tilde of Z is normalized with the mean 1 and has a fluctuation that matches exactly the quarter-Thomas distribution. And this P tilde is what allows us to do the spectral-based benchmark. So this is one slide that's technical, just to make sure all the theorists are happy. So Daniel proved this following theorem. If you have an initial state psi 0 and a Hamiltonian H that satisfy a certain conditions on the distribution of energy eigenvalues, that's the ergodicity condition. And also we assume that this quantity, so some theorists might recognize something similar to the inverse participation ratio, but properly weighted. So this measures the effective size of dimensions. If d beta is very large, then we can show that all the moments, the weighted moment of the P tilde quantity converges to the universal value K. So this particular condition about the resonance is a polar condition. If you have a sum of K different eigenvalues, that's equal to sum of K different eigenvalues of different set. They are equal to one another exactly as long as those indices are the permutation of the other. And there's no other way to have them equal. So this is a kind of a generalized version of no resonance solution. Yeah, but
So even interacting interval systems generically won't have resonances.
You're right. Interacting interval systems satisfy this condition.
So, but you expect interacting interval systems to give you this Porter-Thomas spectrum?
Yes. Yes. However, this d beta quantity might not be as large if you choose the initial state to be highly overlapping with the So depending on the initial state and the measurement basis, if you choose it well so that participation ratio is like large, and then you should see the Porter-Thomas, and then that's verified by the marks.
I see. So then you're saying that instead of just summing over energy, you'll have some kind of generalized Gibbs ensemble type sum for like the Boltzmann factor or won't.
Yeah,
be
it'll be,
able to
yeah,
like
like,
completely
yeah, that's right. It's a quotation mark, that's right. I meant to say some systematic things that comes from diagonal stuff. Yeah, so we are utilizing this hidden speckle pattern. So we use this for the different platforms. So so for the Boltzmann model, formula model, top down, and two different model systems, we assume the relevant decay mechanisms and monitor the fidelity decay. And then the solid line is our estimate, and the dashed line is a true fidelity done in a numerical simulation, and they seem to all agree for the different platforms. So we have a platform independent ways to estimate fidelity. And we actually worked it out. We collaborated with a couple of experimental team at Caltech. And one is this Oscar Painter's group, and they recently developed these 10-qubit superconducting systems coupled to 42 metamaterial resonators that behave in a waveguide. And then realizes effective Boltzmann model with the beyond near neighbor interactions like this. So this is effective Hamiltonian with this. They have interactions, on-site interactions, and then hopping that's exponentially decay, but otherwise the beyond near neighbor interactions. So at the time we wrote this paper, actually this is actually published 5 days ago. So when we at the time we worked this project, we did not have enough capability to estimate the hopping matrix element for every pair ij, because we could figure out the strength, but we could not figure out the phase. So what we did was we tried our benchmarking method based on certain assumption about their sign, and then we do see the fidelity decay. But if you choose a sign configuration, it decays faster. But if you actually choose a certain sign configuration and optimize the value selectively, and then we have a slower decay of fidelity. I'll come back to this point more in the next slide. That way, we not only could benchmark the distinct system, we also could figure out the coupling strengths. So we did the in situ Hamiltonian pattern estimation. I'll come back to that in a couple of slides. And another collaboration is more longer term collaboration with Andres group at Caltech. So here we applied our method for the ripple atom array systems in the so-called PXP model, where near neighbor excitation is prohibited by high energy costs. We started the initial state, all zero ground state, and then quench dynamics and monitor the fidelity. And to do that, we did a threefold comparison. So we have an experiment in Caltech group, and this is a clean model where we assume everything is perfect and everything is beautiful. And the third one is they also developed ab initio noise model for their quantum systems and numerically simulated their noise dynamics and compared against a clean model. So this comparison, we know the true fidelity gap, and also we just emulated our method and estimate the estimated fidelity gap B. But between the clean model and the experiment, we estimated the fidelity gap. The reason we have to do this is because, as far as I know, it is not possible to measure true fidelity in the system and experiment at this other than our protocol. So we have these threefold comparisons, and we see that they all agree and then have a simple exponential decay for 10 atom benchmark systems. So we could estimate the many-body fidelity decay for the analog simulators with the ab initio or noise models.
Sorry.
Yeah.
Question. So what is omega here? Is that a two-body?
No, omega is a single body like and it's a blockade illusion.
So, and this decay is coming from the single body loss?
It's a combination of many different factors that includes laser intensity noise and then the spontaneous decay or the decoherence of the glucose.
I should understand this in 10, is it 10 Rabi cycles?
Yes.
The fidelity is
That's
down to
right.
like
If you had a single particle, what would be the Rabi oscillation? That's the 10 Rabi oscillation. So we are just using it as an. Okay, so this is up to the paper we published recently, but we went further. So we did the same experiment for the 24 atoms and 27 atoms and 30 atoms, and those can be reasonably small, so we can numerically simulate, and then we all see this simple exponential decay. Actually, we went further. We went to 48 and 54 and 60 atoms, and we all see the many-body fidelity decay. And one number that's nice to remember is for the 60 atoms, about if we extrapolate about 10 Rabi cycles, we have a many-body fidelity of 10%. And as a theorist, what I found interesting is these curves are almost perfectly simple exponential decay, which shouldn't be trivial because, in fact, we have an ab initio noise model, and if you eliminate many different noisy sources but add one at a time, in each cases you do not have a simple exponential decay or sometimes Gaussian decay or some other decay. But if you add multiple noise sources together, then you see the simple exponential decay. So this simple exponential decay is kind of emergent phenomena. Sometimes theorists assume this, but this is an interesting fact. We fitted this decay rate as a function of system size. It seems to fit pretty well with the linear curve. So now we can, the take-home message of this is that we have a quantitative way of doing the mathematical fidelity analysis in a scalable way, not scalable, sorry, in the scaling. And also this method is sample efficient. So we use a reasonable in small number of samples. Another thing we tried.
Sorry, Soonwon.
Yeah.
So first, how did you simulate 60 sites? Is it just because your time is not very large?
Yes, the time is now large to use the matrix product space simulations. Only up to that point.
Okay.
We do have a result beyond that time, and we play with the dots. But the holiday is not good, and also we are working on an interesting story for the quantitative comparison of computational cost versus experimental capabilities and so on. So I didn't put it in.
And what was your point about the fidelity? Because it seems natural that your gamma would scale with system size because you make a little bit of error everywhere.
That's right.
That causes some exponential decay
That's right.
in fidelity with n
That's right.
and also with time. So,
That's right.
so what's the surprise there?
So it's not surprising, but it's surprising to see that in the real world because the fact that let me tell you this. How about this? Okay, you result. Suppose we don't work whole systems as a single interacting system, but split them into two different ways. And then what we could do is we do the estimate the fidelity of this guy and this guy separately, and then multiply them. And then compare with the fidelity of the total system that's jointly done together. And they are not equal. The reason being, one of the noise source is this common layer and their intensity noise. So if there's some fluctuations, that fluctuation is common to both sides. So if you naively estimate as if the error sources are independent and then multiply them, the scaling is not working. And we actually do see that in the lab. So from that sense, this simple exponential decay and this linear scaling is a still non-trivial fact. Sorry. So okay, so it's a non-trivial fact in a sense that it's kind of lower large numbers coming into play. Somehow it becomes still effectively, scaling this way, but we don't claim this is. We don't claim errors as non-total. If there are correlating noise, nevertheless we have a linear. Yeah, so we carried this out. We developed a new benchmarking formula. I'm not going to present here. That works also in this case incorporating the correlating noise. This way, we can actually work with the 60 qubits, not only for benchmarking all together, this orange which stops here, but actually you can do the split array and then do the benchmarking together, incorporating the correlated effect. They agree in the regime where we can simulate, and then they also can go forward. And this capability, did I answer your question? So this capability actually gives us some tiny, some basic building block to do something more, a little more. So let's just step back. What are we doing? We have a theory model describing ideal behavior, and we have experimental samples obtained from the experiment, and then compare them, and then figure out the fidelity. What if the experiment is perfectly good, except that our theory model is not as good? Maybe our theory model has some miscalibrated parameters. So what we could do is we variationally optimize some parameters for the initial state and the Hamiltonian to maximize the fidelity with the experiment. And that way you can learn the parameters and then processes. And this has been also demonstrated in the experiment, but I'm not going to present because I want to present something else. So this type of capability can be used in the following way as a subroutine. Suppose I want to prepare some quantum critical wave function at the critical point of the space. So this is a phase diagram of ripple atom chain, and this is a ground state that I want to prepare, many ground state. However, experimentally, we do not know the precise location of the ground state. What we do is we prepare the state and patch tiny bolt by some other Hamiltonian to make it chaotic. and then do the benchmarking with respect to different initial state along those lines, computing the classical computations. And then what we see is that this fidelity estimator is actually maximized at the right point. That way, we can figure out what state you have prepared in the laboratory in this way. Furthermore, let's say actually the state we prepare is not the pure state, it's a state, for example, firmware state. Okay? The firmware state has a calculation for the ground state, and first excited state, second excited state, and so on. What we could do is prepare this mixed state, quench time evolved by some other Hamiltonian, and then do the benchmarking where the theory assumes you prepare the initial state, which is ground state, or first excited state, the second excited state separately, and figure out the probability for each manifold. And then you can figure out the composition of the mixed state in this way. And so this is a numerical simulation version of that, where the true probability distribution is well captured by our benchmarking method, simply by doing the quench time. So that way we can quantitatively verify the performance of analog simulators in the regime that we can simulate so far. So that's the first part of my talk. And any questions so far?
Sorry, on the last slide, why should the fidelity peak at the critical point? Like a physical reason?
Oh, sorry. So here, what we simulating is the following situation. As an emulated experiment, we prepare this state, and then we change the theory models.
You're always comparing to the
same
classically computed critical.
Classically computed. To figure out where we
Where?
Any other question?
This speckle pattern is for the diagonal elements of the density matrix.
Yes, sir.
Is there some sort of speckle for off diagonal elements?
I don't know. Any other questions? Okay, cool. So far, it was just characterizing, calibrating, and then in my view, the most limiting factor is that it's not scalable. We need to simulate the system. So in the regime where we want to learn something new for the large scale quantum simulator, we cannot use this approach. But the second part is addressing those points. So let's talk about this. So in the conventional approach, we do some interesting quantum simulation. Maybe we just generate some superconductivity in the Bose-Hobart model and E-wave superconductivity, for example, and we want to probe this property. However, when we actually perform measurement, basically the only thing you can do is just taking a snapshot. Okay, where do we have particles? In each side, how many particles do we have? This real space snapshot measurement is one of the most natural and basic measurement that we can do. This is already very good. We can calculate how many particles are sites are doubly occupied. We can compute the density correlation, the endpoint correlation. We can stick into the machine learning procedures, and we can do many things. However, that's not all information we want to get. In this way, we only get the diagonal entries of the density matrix between the real space spaces, box space spaces. Therefore, even though we can compute this, we cannot compute many other things like entanglement, Chern number, or transport coefficient. And also, if you want to do some unsupervised machine learning, for example, we do not want to bias the data by just imposing the data in the real space. So what I'm going to talk about in the next slide is resolving distribution. Here is a new measurement approach that we propose. It's extremely simple, and turns out it has been used in a certain specialized version for many decades. So the idea is this. So we prepare the quantum state of interest size system, and then bring extra degrees of freedom right next to it. And this extra degrees of freedom is we assume in a certain quantum state that we know very well. For the case of Bose-Hobart model, it could be just empty sites. Here, I just place them all next to each other, or you can place them on top of each other. It doesn't really matter. So this is just a pictorial representation. And before performing measurements, we again do the natural quench dynamics. Just evolve them in a random chaotic way, so that the system degrees of freedom and the ancillary degrees of freedom all mix in a crazy way, and then perform snapshot measurement of the extended space, and get the snapshot Z1, Z2, Z3, and Zn. And that's all we have to do on the experiment side. On the theory side, we are going to do the following. Suppose we are interested in evaluating the observable flow, the operator observable flow. And then what we do is we take this as an input, and also this natural dynamics as an input, and do the classical pre-processing. And the output of pre-processing is what I call as a computationally assisted observable, O of Z, small O of Z. And this small O of Z is different from large O of Z. It is essentially some real number attached to every measurement outcome that you could have obtained. Okay? And we designed this small O of Z such a way that if you average this small O of Z from the samples obtained from the experiment, that converges to the expectation value of the observable with the quantum state of the system. So we designed this observable in this way. And in this way, we can probe arbitrary properties with the same set of experimental data, just changing our classical data processing method. At the same time, I'm going to talk about how to measure the not in diagonal or endpoint correlation, but off diagonals, even nonlinear observables like entanglement or Chern numbers or transport. And in principle, this approach contains everything that depends on the density metric system. So it's a good way to stick into the unsupervised machine learning. So how does it work? So what's the idea? So the idea is to utilize operator spreading and information spreading. It's a fancy word, but in reality it's very simple, so let me explain. So suppose we prepare a quantum system of interest and we have a density matrix group system. This is essentially a matrix that's D system by D system. So what we do is we bring the ancilla and then expand the system and perform measurements and obtain the outcome probability distribution, which has a D extended. Okay, so it's a larger Hilbert space dimension because the system is extended. Okay? And there must be a map related by the scrambling dynamics that maps this density matrix to the probability distribution. And if this map is sufficiently ergodic and chaotic, and also if the number of entries here, D extended, is larger than D system square, and then with the high probability, this map is reversible. So we can talk about this recovery map R. And whenever this R exists, this protocol is homographically complete. What it means is that if you know this density, this probability distribution, we can apply this map such that we obtain the density matrix. So we can in principle figure out exactly what the quantum state is. But as I described earlier, figuring out and then doing the tomography is fundamentally very difficult and requires many measurements. So instead, what we are going to do is not doing tomography, but designing this computation observable such a way that it averages quickly, this quantity averages quickly to the desired observable. And then in this way, it works for any complicated observable because in principle, this histogram has all information about the density matrix. Any question? Okay. So there's another way to see this picture, maybe more favored for some theorists here, and that's the comparison to the randomized measurement. So the randomized measurement is something I mentioned already, and it's the following idea. Suppose we have some quantum system of interest, orange boxes, and instead of performing measurement directly, we apply random unitary and then measure. And then with some clever data processing, we can extract many different forms. And this is essentially what we are doing. So here, this is a circuit diagram of what we are doing. We have a system of interest rho, and so ancilla state, now representative is like the zero state, and involves some natural chaotic dynamics. And then measure everything and then denote it as Z. But conceptually, we can think of it as two different measurements. One performed on the ancilla, the other one on the system. And then conceptually, we can think of as if we apply measurement on A first and condition on A, this whole dynamics is doing some crazy linear transformation on the density matrix. And then we perform measurement S. Therefore, you can think of it this way, the rho undergoes a linear transformation M that depends on the measurement outcome on A, and then we measure S. So for the different measurement outcome A, this MA is just crazy random unitary. Therefore, it's basically performing randomized measurement. The difference is here, the use what I decide to measure. I just choose U. Here it's randomly chosen, but that doesn't make any difference for the data analysis. As long as you just do random measurement, doesn't matter. The choice of having to choose a certain measurement doesn't really matter. So from that,
when you say random measurement, you mean just measure each qubit in a random basis.
Or apply semantically gauge and then measure.
So I think the problem you're trying to solve is that if you have a deterministic H, then you can't measure it in random basis. So you're introducing the randomness by measuring the ancillary difference.
Absolutely, yes, yes. The extending the little space allows us to rotate in a different place. So in that sense, we are doing kind of chaotic measurements because you rotate in a chaotic way. And this is too simplistic picture. There are many more important questions that we need to answer. For example, is this approach computationally efficient? You know, if we have to simulate the whole dynamics to the expected measurement, what is the point of doing this? And sample efficiency, like those systems, requires like from 1 second to say 1 minute to obtain one data sample. So we want to minimize the number of samples that is needed to estimate observable. And also, can you actually guarantee that any observable can be measured for the role of symmetry or the robustness of the noises? There are many questions. So if you're interested in, please see our paper for those 3 items. But I'll make some comments related to this first two. The short answer is it's reasonably good, in a sense that it's as good as the state of the art in a certain cases, but not always. So I'll elaborate in the next video. Okay. So one way to see that is the following thing. So here I explain as if the system, the orange degrees of freedom, is scrambled with the ancillary degrees of freedom in a global quench dynamics. But this doesn't have to be. If you have a system like this, we just divide into the different subsystems, and you can do the quench dynamics so that each subsystem is not talking to other systems and talks to their own ancillary systems, and then perform measurements. In this case, the numerical simulation that we need to perform is a quench dynamics of individual patches separately. And then we can invert the formula later. So if you do this quench, this is computationally more scalable. However, this is not always the best, because depending on which way we do, the different observables require different number of samples. For example, based on our intuition to the this randomized measurement literature, more rigorous analysis can be done. If you do the global quench, you need to simulate the whole dynamics. However, the row rank observables such as like fidelity can be efficiently estimated in number of samples. That's good for verifying the state declaration, as we did in the part 1. But if you want to observe only few body observable at 2-point correlation function, regardless of their distance, can be very efficiently measured within this path quench. But this is just a quick example. We can talk about different systems as long as you bring in this extra degrees of freedom. It doesn't even have to be a separate particle. Say Ripple atoms, suddenly you somehow realize their motional degrees of freedom, the nucleus spins, just somehow make sure to introduce new dimensions to the Hilbert space and then engage them, and that's really helpful. And also we can think of a more funky way of introducing this patch. For example, if you have a Bose-Watt model like this, the 2D lattice geometry, we only couple the subset of the system to some other layer in the Z directions, and then make them tunnel by themselves and interpolate. So this kind of geometry has their own sample complexity, the number of samples and complicated. So this is a comparison. Our protocol is related to this randomized measurement or so-called shadow tomography. The difference is that we use only one natural geometry, but they have to tune this fine-tuned geometry. The sample complexity is the same. The difference is, in the case of the global quench, our system doesn't work because inverting the whole map is computationally costly, but this one is simplified one. So we also have done some theory results. So I'm not going to go into the detail, but please see our paper. So some connection between chaos and then tomographic completeness. Turns out there's a very trivial relation between out-of-time order correlators to tomographic completeness. And also, what is the necessary time they need to evolve so that this approach works? And that's basically determined by the number of ancilla that's visible to the system, determined by this Lee Robinson velocity effect of light tone. And when it comes to inverting this data, this R recovery map, turns out it's not unique. You have very different maps. So we figure out, Daniel, my student, figure out the optimal way to post-process in terms of minimizing the sample complexity. And also we analyze what happens in dynamics is Okay, so any questions?
What do you mean by the dynamics?
Yeah, so here we do the quench. Again, we are utilizing this kind of quench dynamics here. And this quench dynamics. What if this is open system dynamics? In 2 different cases, we know what the noise model is, And two, we don't know what the noise model is.
You're saying you're adding dissipation, or you're adding a shot by shot variation in a unitary?
Both. And then our analysis is a twofold. If you know what's gonna happen, just define that as our channel, and then just revise our inversion formula. If you don't know a priori what the errors are, and then you could have a systematic error, but we show that does not lead to any catastrophic divergence event. There's no instability, just reasonable. So like if you have epsilon noise error, the systematic error is 4.2. Okay. Any other questions? Okay, cool. So let me spend a few more minutes. So that's all content, but let me spend a few more minutes talking about specific example they worked out. So
Can I ask a question?
Yeah.
So how much bigger does A have to be, or how many bits in that P vector do you need?
We want to double the Hilbert space, so the number of degrees of freedom has to match. Yeah, so 1 cubic basically 1 or 2 cubics.
You can't do anything with smaller.
No, the reason being we are essentially measuring diagonal entries of the extended system. That number has to match with the number of coefficient in the density, which is the system square. The extended dimension has to match the system size square. So in case you say Bosolov model, for example, is kind of tricky because we have a total partial number conserved. So bringing in empty side doesn't mean it's doubling the space scales in different way. But the answer is the dimension after quench has to be as large as the dimension square. Okay. Cool. So we elaborated 3 different examples in our manuscript. So please take a look. One example is we considered Bosolov model and then explain how to measure many-body changes from the snapshots. The other one is Fermi-Hubbard model, and then we talked about how to distinguish S-wave superconductor versus D-wave superconductor. The third example is a Wittgenstein chain, and we showed how to study energy diffusion dynamics using our approach. But today, let me actually focus on the middle case, the second example. Okay. The Fermi-Hubbard model is maybe one of the most well-studied theory models and actively pursued in the cold systems because it may actually give us some solutions to the high density superconductivity. So this is the proposed phase diagram of the Fermi-Hubbard model, and then we recently observed this in a one-way anti-parameter library. The goal is to understand whether we do have D-wave superconductivity in other concentrations. But this is theoretically also a challenging problem. There are debates about whether this really have D-wave superconductivity in the bare Fermi-Hubbard model with some modifications and so on. And this is where our quantum simulation, it could be very useful. At the moment, we do not reach the low enough temperature to see this, but maybe we will within a few, in the near future. And there are experiments where we have already realized both the Fermi-Hubbard model and the long-range electromagnetic order, so maybe we can lower the temperature further. But when the time comes, we need to ask how to figure out the superconductivity we obtain is actually S-wave versus D-wave. So can we actually, do the more detailed analysis? The problem is distinguishing those two is not so easy in the current measurement method, because these two superconducting order parameters can be characterized by superconducting pairing order parameters. For example, this is a second quantization language like annihilation, creation operator, 4-point correlation function. And their positions are I, J, K, L. So here I consider the example I and L being the same side of K, L here. And then if you measure this 4-point correlation function for different spatial profile, and in the S-wave case, we have this kind of S-wave symmetric landscape, pairing landscape, or here the D-wave landscape. And we are to distinguish those two, but those observable is obviously off-diagonal entries because creation and annihilation act on different sites. So this is not measurable in the existing capability naively. So our task is to distinguish S-wave versus D-wave. And how to do that? We choose this as an observable, and then we do this bridge patch scheme. So suppose we create some quantum state of interest. we consider two different local sites and then tunnel through to another layer in the z direction and then interfere them, and then measure the snapshot of maybe everything or the particles on this. And then do the classical data processing we proposed. And then this is a numerical simulation of that situation. If you have about 1 million samples, we can figure out this entire profile. A million samples is still like too many samples. If you put into realistic numbers, it takes, I think, if you assume 1 minute per sample, that's a very long time. But if our goal is to just distinguish them, we can identify difference between those two and then to figure out which one is more competitive between the two. And depending on the two cases, we have this different histogram. So using this Witness method, we can distinguish S wave versus D wave within reasonably small number of samples, say 2,000 samples. Yeah, so that was an example that I wanted to elaborate and to summarize. So we talked about benchmarking based on hidden spectral pattern, and that was allowed because we could identify this universal phenomena, the hidden spectral pattern, and we demonstrated the two different experiments. And we talked about extracting arbitrary properties based on the operator scrambling. And we are thinking about developing further as a metrology scheme, or maybe talking about quantum advantage based on analog simulators. And also, in the future, I believe that our quality of the quantum simulator should become better and better. And maybe you can produce data that go on a public library, so that rather than benchmarking quantum devices, maybe in the future we can benchmark classical simulators based on the experimental data, which is basically one of the projects that we are pursuing together with others. One take-home message that I want to give you is that even though the system may behave chaotically or logically, once we have a knowledge about them, and with the proper classical computation, they can turn into the application. So that's what I want to emphasize. Thank you so much.
So you mentioned that for this second scheme of measuring an arbitrary operator, it was more practical if you only had to mix ancillas with a subsystem. What's the computational scaling with the number of ancillas, for example?
Yeah, if you do like this approach, so you only do the patch here, the computational cost is the number of patches times Hilbert space dimension of this each patch.
Oh, okay.
Do some polynomial, maybe square root of that. Yeah. So it's a scalable approach in a sense that once the patch size is fixed, then
Does the addition of the ancilla like qubits need to be simultaneous, or can you do it sequentially?
Sequential.
Can you clarify what you mean by that?
So maybe like I assume that your question is whether you need to bring this ancilla and this all together, or do this and then do this and do this, right? It doesn't matter as long as in the meantime they are not interacting. Then it's okay.
Yeah. So how long do you need to interact with the ancillas for? 1 pi time.
So in this particular example, for example, time long enough so that information on here propagates to here. So here like two pi in a sense.
So that means if I have a many body localized system, I might have to wait a very long time.
That's right. Or the accuracy will go forward. So you want to have an orthogonal system.
One question. So for the D wave versus S wave, when you do this switch sequential, isn't that something like I would anyway do naively if I say I want to measure this correlator and I want to measure the interference between this?
Yeah.
So why do I have to go into this theory, like into this more complicated theory? If I can anyway do this, that I can couple these systems and let them interfere, don't I get it directly without going into the randomized measurement?
Also, nice, it's a good question. So you're asking if you have a capability to design this particular L-shaped tunneling and their interference, why not just directly interfere them and then directly measure this particular photographs, right? That's your absolute point. Here, this is L-shape as an example. One thing you can think of is the following idea. you have this prepared, and other than these two parts, blow away all the items. Right? Because they're not gonna matter. And then turn on the tunneling and then they are interacting with this on plane. That's kind of easier. I just made up the one other situation, but this is an example, but do whatever, you know, whatever that you can do in the lab. Did I answer your question?
I was just curious, so, is there a way that you can, like, a thing that comes up often, so measuring the fidelity is really nice.
Yeah.
Another thing that would be nice would be if I could measure sort of, like the error, so I know what state I'm trying to make, I made some particular state, and I wanna know, I would like to do like a density matrix reconstruction of like the difference between those two.
That's right.
Is it like, is there a natural way of taking, these sort of protocols and doing that?
Yeah, so that's also a very good point. I don't have, honestly, I don't have like perfect answer for you, but I can talk about something potentially related. So here, for example, let's assume that it's not incoherent, it's supposedly coherent. Namely, our Hamiltonian parameter is something that we don't know perfectly. And then we do the benchmarking pass, and then do the different numerical simulation for the different parameters and try to optimize. And then we can figure out the Hamiltonian parameter. So this is a version of quantum process homomorphy, assuming this is always in nature. And let's take one more example. And I show you this, but maybe I can. So here. So in the third example, we are essentially doing the tomography within the low energy matrix. Suppose we can measure the overlap between a certain state you prepare in the lab and some theory state that you can change. And if you have some candidate states that you can test against, you just change the theory state in all different states. You're just measuring overlap. So we can not only measure here I'm applying the population. I have not tried, but I suspect that it should also work if it's a superposition state. And that way you are essentially doing the tomography within this manifold of the candidate states. So that way you can figure out the density matrix and probably some hints about the noise.
I have a question for you. I think it's sort of in the same family. So my understanding is that sort of the game is generically what you're trying to do is spread all of the coherences into the measurable degrees of freedom and extract it from the spectrum.
That's right.
Right? So that you don't have to measure the coherences.
Absolutely.
And at some level, it sounds like this requires some amount of knowledge of what the underlying model is.
That's right.
So what if what I want you to do is distinguish between topologically ordered and non-topologically ordered antibodies? I want you to measure the antibody number. Is that a sharp enough question, or do you need to know exactly what model it is for looking?
I mean, aside from my talk, if you're literally asking me, I give you the wave function and tell you whether it's topologically ordered or not.
I want you to tell me.
You give me the wave function, or
I give you a system and I want to make speckle type measurements.
Yeah.
I want and for you to tell, and make it local unitaries or something, and you tell me whether it's topologically ordered.
Yeah. It's proven that it's not possible. So the reason being, this definition of topological order is basis independent, and it's more about the entanglement structure.
Yes.
And therefore, if you just perform measurement, you can learn about some entanglement structure, but the measurement outcome is always basis dependent of those. Right? So if you do each copy you perform measurement and you give me the data, then I cannot, learn about topological property, probably, in general, unless I have a priori some model. Okay, maybe your model is close to some kind of dynamo model, Fourier model. Then, based on knowledge of that, I can come up with some better heuristics. But if I a priori have no idea, then you just tell me the data, and you describe what you've done, and then you tell me the data. There's strictly no way to identify it. However,
how specific do I have to be about the model? If I tell you that I only have local couplings or something, or local interactions, is that enough?
It's not about the measurement, but the kind of approximate version of the state.
No, I'm saying the Hamiltonian corresponds to some model that only has local interactions.
Does your claim is to figure the ground state of that Hamiltonian? Yeah.
Or something near the ground.
I think it's proper to say to open.
Sorry, so one thing. I mean, say for the Tory code, you can measure some Wilson line operators.
That's right.
And those those are just measurement, those are
That's what
observable.
we're going to.
But
The
they're just
threshold-
saying you know the model.
Yeah,
Okay.
if I'm not told, suppose I'm not told it's story code.
Right,
Or I'm told it's story code, but I don't know whether it's Z basis or X basis. Suppose it's like a randomized basis. And suppose that's even randomized on an individual site level, for example.
you can use randomized measurements to measure entanglement entropy, right? I thought some of the things in.
Yeah, that's right. But that requires exponentially many data. So I don't count as kindness before. That's almost like doing tomography and then compute entanglement in terms of sample complexity. However, if you have two copies of the same wave functions and then interfere them in somehow and then do some random measurements, then there's a hope. And then you can, it's not proven, but there's a hope.
And how identical do the two copies have to be?
They'll reduce your contrast of the if you could develop the method, that contrast will decrease.
No, you develop.
Okay, if I develop the method, that's my expectation.
All right, do we have time for one more question?
So suppose the system you're trying to calibrate is open system, can you use this scheme, for example, to like try to extract the link-lab parameters?
So far, no. So our approach so far it works only for the pure state dynamics. For the same reason, the spectral pattern doesn't exist in the one. We can perceive generalizing our approach for the open system dynamics, but we haven't done it.
Okay, well, if there are further questions, please come talk to Soonwon afterwards, but let's thank you.